right, so we've gotten a little behind, and so I wanted to give you a video introducing simple harmonic motion. So hopefully we could sort of then dig into problems and trying to apply this material for class on Monday. The first thing that I want to mention is there's some common abbreviations that are used when we talk about simple harmonic motion. You might see the abbreviation SHM, which is going to stand for simple harmonic motion, or sometimes you see SHO, which stands for simple harmonic oscillator. They're really interchangeable, and I'll probably use both of them sort of randomly, so I wanted to give you a heads up so you don't get confused. So here is a list of our anchoring concepts. The things that I want to really kind of concentrate on in this particular video is really introducing the idea that this motion that we're going to talk about is the kind of motion that we see when we have a mass on a spring and it's bouncing back and forth between its endpoints and moving about what we would call its equilibrium point. This is a classic example of simple harmonic motion. There's going to be a number of different new constants that we have to learn, and so this might be the challenge, that there's these totally new things that we need to be familiar with, and we'll look at those. And then I want to look at the relationships between the motion of this oscillator, its velocity, and its acceleration. So basically, this video is going to really be concentrating on this first learning objective, where we're going to be talking about the basically how we come up with the expression that describes the motion, and also those different quantities that you saw in that previous slide, like angular frequency, frequency period, amplitude, all that good stuff. So cute dog picture for attention. So there is, simple harmonic motion is a sort of a subset of periodic motion. Anything that is periodic is something that like happens again and again over a predicted amount of time, which is the period. And so it could be sort of the swinging back and forth of these little dog legs as they're walking. It could be the motion of a planet moving around the sun, the rocking chair, a bouncing ball, and so that would be periodic motion. We're going to be more specific. We're going to talk about a specific type of this periodic motion, which is simple harmonic motion. So it does have the repeating path of motion, and it is periodic, which means it takes a certain amount of time for that repeating motion to occur, and it's going to always take that same amount of time. But what makes it specifically simple harmonic motion is there's going to be an equilibrium location, an equilibrium point, and the motion is occurring around that point. So the two examples that we're going to think about that are simple harmonic motion are the mass on a spring and a pendulum. So in both those cases, a pendulum, its equilibrium location is when the pendulum is hanging straight down, but you know that a pendulum swings back and forth in its motion, and so it's moving about that equilibrium location. Similarly, a mass on a spring, we've already talked about that when a spring is at its natural length, that's when we say that x is equal to 0, and that becomes the equilibrium location. But if we stretch the spring and let it go, it's going to pass right through that equilibrium position on its way to compression, and then it'll go back to being elongated. And so that's the predictable harmonic motion that it's occurring around that x equals 0 equilibrium point. So let's take a look again at that mass on a spring. So here is a picture of the mass on a spring. This right here, x equals 0, is the equilibrium location. So that's where x equals 0. And then we know that if we stretch the spring, we measure this distance here would be a positive x. And the force of the spring is minus kx, so it tries to bring it back to equilibrium. It will move all the way through the equilibrium location, but it's moving when it gets there, so it keeps on going. And so then as it's compressed, this is a negative x, and the force again is towards the equilibrium location. So we came up with this expression. We've seen it multiple times throughout the semester. The force that the spring exerts is equal to minus kx. That k is the spring constant, remember. The minus sign indicates that the force that the spring exerts is always opposite to the direction of the displacement. And for that reason, we call this a restoring force. The idea being that the force of the spring is trying to restore it back to equilibrium. Here is a graph from your book that is showing you the motion of a mass on a spring. We kind of start off up here when it's fully stretched. And so we're actually using this term A, which was in one of the slides, as a new term that we're going to learn. A, we're going to call the amplitude of the motion. And this is going to be a term that we will be using in describing this motion. So what we've done is we've started the mass on the spring up at the maximum amplitude, and that's when our t equals 0 right here. And so at that point, the force that the spring exerts is equal to minus Ka. So it's trying to put it back into equilibrium, which is the equilibrium location is right here. And the mass on the spring is going to move to the left. And we can see there's also, as we go down, you can see that the time is being indicated. Notice that at half the period, so again, we see another term, t, is going to be the period of the motion. And that's going to be the amount of time it takes it to go through one complete oscillation. Notice that when t is equal to a half a period, the mass is at its maximum compression. And so you can see it's kind of moved through half of its motion. And then it's going to come back towards equilibrium and go all the way past and come back here at t equal to the period. It gets back to where it started from. So notice that from this location to this location, it's gone through one complete oscillation. And the amount of time that it took it to do that is equal to the period. This is a picture of a graph of simple harmonic motion. Essentially what we've done is we've taken the graph that you saw on the previous slide and we've rotated it 90 degrees because this is actually more common how we would see this motion being illustrated. And so the vertical axis, you notice, is the position of the mass on the spring, and the horizontal axis is the amount of time. And here we see that as we go from t equals 0 to t equals the period, it goes through one complete oscillation. Notice that if I took this piece of the graph and I just kind of kept pasting it as I went over to the right for future time, that it's going to end up to look like a sinusoidal graph, like a sine or a cosine. And that's exactly true. And it means that if we want to come up with some equation that's going to describe the motion of a simple harmonic oscillator, we can either use a sine or a cosine in order to do that. So let's talk about how we come up with that expression. So we're going to go with the idea F equals ma. And remember that the acceleration can be expressed as the second derivative of position with respect to time. And the force that we're going to be using is minus kx. It's the force of the spring. So this is equal to m times the second derivative of x with respect to time, because that is how we can write acceleration. And remember, I wanted to figure out what x was, so I'm going to write x is equal to minus, sorry, I want to do it the other way. I want to write d squared x. I'm going to write the second derivative of x with respect to time is equal to minus k over m times x. And so you probably are looking at this and thinking, you know, what the heck? This is a differential equation. I don't know how to do that because I haven't taken that course. And, you know, this is ridiculous. But let's just kind of stop and think about this for a minute and realize that we're perfectly capable of figuring this out if we just start thinking about it. It's telling me that x, which is going to be how I represent the motion, it has to be some sort of function or something. But if I take its derivative twice, that's what's happening here, I basically get the function back again, but there's like a constant out front. And then I'm like, okay, what have I learned that any functions that when I take their derivatives, after a while I get them back? And maybe I'm like, I have no idea. But then also, let's think about the motion we're trying to describe, that it goes between two endpoints, like a plus A and minus A, and it just keeps repeating, going back and forth and back and forth. And maybe at some point, I'll think of sine and cosine. Because remember, if I take the derivative of a sine, I get a cosine, and if I take the derivative of the cosine, I get minus the sine. And something happens similarly, of course, if I do cosine. So if I take the derivative of a sine or a cosine twice, I get that function back, and there's going to be a negative sign in front of it. And so our solution can be written in terms of a sine of something or a cosine. And to be honest, depending on your book, some books tend to use sine to represent it, this simple harmonic motion, and some use cosine. It really doesn't matter which you use, but we're just going to stick with whatever our book does. And our book uses cosine. And so basically what we're seeing here are the different ways that we can represent the expression for the simple harmonic motion. The first one is kind of keeping it simple. And we're going to start to see some of these terms or these symbols or these new constants that I have to remember what they are. Remember, we've already talked about A was the amplitude of the motion. We've said T was the period of the motion. We might say omega. I've seen that before, and I called it angular velocity. In this particular expression, we're not going to think about it so much as angular velocity, although it really kind of is. We're going to call it the angular frequency. And finally, phi, we're going to call a phase angle. So a lot of times using this expression for the position of our simple harmonic oscillator is going to be good enough. But every once in a while, we're going to need this expression where we have a phase angle. And so we want to start thinking about what all those different constants mean. And so we're going to explain that. So let's look at these expressions, these different constants, and remind ourselves what they mean. So the first thing I want to talk about is Let's just think about a graph at x equals a cosine of t. If I was going to graph that, if I wanted to graph a cosine function, it starts at 1 and then oscillates between +1 and -1. So this is +1, then this is -1, and this represents 2 pi, or 360 degrees, because it takes 360 degrees for the cosine function to go through one complete oscillation. If I change this and I write x equals 3 cosine t, what changes about this drawing that I drew up above? It doesn't affect the fact that it takes the cosine function 2 pi radians, or 360 degrees, to go through one complete oscillation. But what it does change is the amplitude. And so a cosine t, you can see that what this means is the amplitude. And so for our mass on a spring, that term a that goes out in front of our expression for our simple harmonic oscillator is simply like, what's the largest displacement that the mass is from the equilibrium location? That's the amplitude. It's going to be measured in meters usually, but sometimes you'll see an expression where it'll actually say like 3 centimeters times the cosine of whatever. Okay, so that's what that a means out front. What about the omega? So again, I said x equals cosine t, and I said that when I graph it, this is 2 pi. So what happens if I write x equals cosine of 4t? This isn't 2 pi anymore because of that 4 in front of the t. This angle right here, which remember, this represents t and this is x here. And in this picture, because I didn't put anything out in front of the cosine, this is 1 and this is -1. But now, to go through one complete oscillation, 4 times t has to be equal to 2 pi, which means that the time here is actually going to be 2 pi over 4. So what am I getting at? Putting this value in here makes the function like go through one oscillation faster. And so whatever the number is, like here it was 4, it went through the oscillation 4 times faster. And so when in our expression for the oscillator, the number that I'm putting in front of here is this omega, which I told you is the angular frequency. That's what we're going to call it. And it still has the units of radians per second. And, well, that's something we need to know, because this angle is going to be expressed in radians. And this is the first time that if you do a calculation where your radiation, I don't know why I wrote that, radians. If you do a calculation where you have to figure out, calculate x, the angle actually does have to be in radians. Anyway, so we call omega the angular frequency. And basically what it does is when you put it in the equation, it's helping your equation mimic the mass on a spring so that it oscillates at the correct frequency, so that it goes back and forth between its oscillations just as fast as you've observed. And finally, the idea when we saw the most complete expression for the simple harmonic oscillator had this angle in here, which we call a phase angle. And that's basically, again, the whole point of everything we're doing is we're trying to write an equation that will tell us for our mass on a spring what would be the x position at any time. And so it's really trying to mimic the physical situation of this mass going back and forth and back and forth, so that if you put in a time, you know exactly where that mass is. And depending on how we start the oscillation for our mass on a spring, it might not actually start at t equals 0 at being at its maximum displacement, but maybe it's somewhere else in its oscillation. And that's when we have to introduce this phase angle to basically just shift the cosine function over a certain amount. And so this is our shift, which is due to our phase angle. So that's what that is for. So here we are sort of summarizing this expression that we use for our simple harmonic motion. A is the amplitude, and it's the maximum displacement from the equilibrium of the mass on a spring. The period, t, is the time that it takes for the system to go through one complete oscillation. Frequency, which I think we've seen that term before, frequency is basically how many oscillations there are per second. It's going to be measured in hertz. So this is number of oscillations per second. The angular frequency is 2 pi f. And that's a relationship we're going to want to remember. And then finally, the frequency and the period are inversely related to each other, so that if I can figure out what they are, then I can find the other one. And something that I forgot to mention when I was showing you how you got this expression, remember we had d squared x dt squared was equal to minus k over mx. The thing I forgot to tell you is we consider k over m to be actually omega squared. So omega is actually predicted by the spring constant of the spring and the mass that is attached to it. So that's kind of important. It's something I completely forgot to mention. And this is another relationship. So you can see, like, I think understanding a mass bouncing back and forth as it's oscillating, like visually and, you know, in our experience, I think that's not that bad. The big challenge here is there's just a lot of new expressions that we have to be familiar with. You know, we have to kind of work to become more comfortable with those. And so here's some other relationships. Because omega is related to the force constant and the mass of the object, we can, and also because regular frequency is related to the angular frequency, we can also express frequency and period in terms of the mass on the spring and the restoring force, or the spring constant. So these are other relationships. To be honest, I like to kind of keep it simple, and maybe I don't have this expression in my brain that I memorized it, but I know that omega is the square root of k over m, and I know it's equal to 2 pi f, or 2 pi over period. And then for me, this is good enough for me to allow myself to just rearrange these expressions to solve for frequency and period in terms of k and m. So again, here we're looking at the expression for our mass on a spring. Again, the amount of time it takes to go through one complete oscillation is its period, and A and minus A represent its maximum displacement from the equilibrium location. So let's talk really quickly how we would find expressions for velocity and acceleration of our simple harmonic oscillator. So I'm going to just start off with x equals a cosine of omega t plus phi. And I know that velocity is the derivative of position with respect to time. So I'm going to take the derivative of the cosine. Derivative of the cosine is minus the sine, so I get minus a times the sine of omega t plus phi. But then I have to use the chain rule, so I have to take the derivative of the angle with respect to time, and so that gives me another omega. So I might express this as a minus omega a times the sine of omega t plus phi. And so that's my expression for velocity. If I want to find the acceleration, it's the derivative of velocity with respect to time. Of course, it's also the second derivative of position with respect to time. So if I want to take the derivative of this expression right here, I'll just put, I have minus omega times a, and then I want to take the derivative of the sine, which gives me the cosine of omega t plus phi. And then I have to take the derivative of the angle with respect to t, which gives me another factor of omega, so I'm just going to get a squared in here. So this is what my acceleration looks like. If I do a comparison between position and acceleration, I can say that acceleration is just minus omega squared x. One other thing that I might want to do when I'm looking at these expressions is I might notice that whatever is out front here represents the amplitude of these particular values or their maximum values. So I would say that the maximum velocity is going to be omega times a. And when I look at this expression, or this one really, my maximum acceleration is going to be omega squared a. And so those are important or helpful things to remember. Here is a graph of how the velocity and the position are related to each other. I think that it might be helpful to compare particular locations. For instance, when our position is at a maximum amplitude, if we kind of go down, we find that at that location the velocity is 0, which should make sense to you, because if the mass on a spring is oscillating back and forth, when it gets to its maximum displacement, it's actually turning around. And so then it has to be then have a velocity of 0. In the opposite case, when it has 0 displacement, like right here, if we trace down, we see that this should be corresponding to when the velocity has one of its maximum magnitudes. And so again here, these graphs don't seem, I might have pasted them in because they don't seem to be matching up exactly, but believe me, this is what's actually happening. Then finally, when we compare the position and acceleration for the simple harmonic oscillator, these are actually, it is kind of nice because remember the acceleration was just equal to minus omega squared x. And we can see that these two graphs are exactly negatives of each other. And then of course, then the magnitude would be opposite as well. So what are we finding? We're finding that when the mass on a spring is at maximum amplitudes, we actually have also maximum accelerations, but they would be in the opposite direction of what the displacement is. And yeah, so that's just thinking a little bit more about the how the speed and the acceleration and the position are all related to each other. to be honest, I find it a little bit easier to think through these when we're thinking about it from the viewpoint of energy, which would be a different topic.